So this problem asks us to apply Biot-Savart's law here to a simple situation of a current carrying wire in order to find the magnetic field at some point distance a away, and we call that point P. So we first start with Biot-Savart's law, and we're going to break down this expression little by little so we can fit everything in terms of one variable that we can integrate. And that variable that we're going to integrate along is the angle theta. Now you could use this angle here, but it just seems more intuitive to use this angle theta, and we're going to integrate from one side through 180 degrees all the way to the other side. So the most complicated part of this is the ds cross r. So why don't I look at that real quick first. ds cross r. Well, this is a cross product between two vectors that results in another vector. So the result of this is going to have some magnitude and some direction, which will be given by a unit vector. So we need these two pieces of the puzzle. Well, probably the simplest thing, or I guess the quickest thing, is to first talk about the actual direction. So we need the vector ds, and we need the, oh, I'm sorry, this should be r hat, not r. That's a mistake I made. So where is ds on here? Well, this ds is this infinitesimal piece of the wire along which the current is flowing that has some direction in the direction of the current. So this is ds right along the wire. Now what about r hat? Well, the vector r points from this infinitesimal element to the observation point P, and r hat is just simply the direction of r. Using the right-handed rule for cross products, you point your fingers in the direction of the first vector, which is ds. You curl them in the direction of the second vector, which is r hat, which points to P, and your thumb points in the direction of the cross product. Alternatively, you could use your index finger in the direction of ds and your middle finger in the direction of the second vector, r hat, and your thumb points in the direction of the cross product. Now, the problem with this method is that sometimes people reverse the two vectors. Your index finger always points in the direction of the first vector, middle finger points in the direction of the second vector, thumb is the product. You can eliminate that mistake by using this other method of saying point all your fingers in the direction of the first vector and move them, curl them in the direction of the second vector, and then their thumb points in the direction of the product. So since we know that the magnetic field is going to have the direction out of the page, and that comes from the cross product here, we can say that that has the direction of k hat, positive k hat. Okay, so now what is the magnitude of the cross product? Well, we know that can be found from the magnitude of ds times the magnitude of r hat, and that gives us the magnitude of the sine of the angle between them. Call that phi dsr. So the cross product ds cross r hat is equal to just ds. The magnitude of r hat is 1. Notice I dropped the vector bar to indicate the magnitude here. And this angle, phi dsr, that is this angle here, phi dsr. Can I put that in terms of theta? I mean, yeah, you can. You can say that is 90 degrees minus theta, which phi dsr equals 90 degrees minus theta, because this is a right triangle. So if this angle is theta, this is 90 minus theta. There you go. So the reason I did that again is I wanted everything in terms of this angle, and that's what I eventually went to integrate over. But is there a more elegant way of putting this? Yeah. Sine of 90 minus theta is cosine of theta. That's just a property of geometry. Oh, and I forgot my k hats here. this vector, I can leave off the 1 now. The magnitude is 1. ds, since this is along the horizontal, let's just call that dx. So say ds equals dx. So ds cross r hat equals dx cosine of theta k hat. So far so good, right? Except that the x is going to be changing in this problem as you're moving along this wire. So now I've got two variables that are changing, but the two relate to each other. Dx depends on theta, so how could I relate the two? Try to combine them so that they're both a function of theta instead of having two variables here. Well, I can relate x to some other stuff, so let's say I want to sine of theta, for example, is opposite x over the hypotenuse r, right? But now we've got r into the picture here, and that doesn't help us a whole lot because now r is going to be another variable. If I solve for x and put it in terms of r, well, then I've got to somehow relate r to theta. So that's not where I want to go. If I look at cosine, I get a over r. Well, that doesn't help me with x. So what if I look at tangent of theta? Well, that is opposite x over adjacent a. And I'm just talking about the whole distance here of this triangle x over this whole distance a. So then x equals a tangent of theta. Now, the way your book does it is they say that x is negative a tangent of theta because we're on the negative side of the origin, where the origin is right here under P. There are different ways to do this, but I'm just going to go with what the book says and say this is negative. Now this will get, I think, a little bit more confusing when we talk about the limits of integration, but so be it. So now I've got x, but I need dx. So I can differentiate dx with respect to theta. We've only got one variable, so I can do that. And end up with negative a secant squared theta. How did I get that? Well, you just know that the derivative of tangent is secant squared. If you don't know, you look it up in a table. If you want to know why, ask a mathematician. I believe this is something we learned in calculus class. So, yeah, you can look it up in the table for this class though. So then dx is equal to negative a secant squared theta d theta. So let me go back to this expression and say ds cross r hat equals negative a secant squared theta cosine theta d theta r hat. I just moved the d theta to the outside. Okay. So I think we're pretty good on this part of Biot-Savart's law. We have everything in terms of theta. We can integrate. Now we've got that r we've got to deal with, because remember, r is a variable. It's changing as you integrate along this wire. So we need to express that in terms of theta as well. So I can say r, the hypotenuse, just magnitude, no direction, is equal to x squared plus a squared. But now I'm back into the x business again. So I would have to do some more to deal with that. So let's not go there. We can say, though, that r is equal to a over cosine of theta. Remember, because cosine of theta equals adjacent over hypotenuse. So I can write it like that. If I wanted to, I know Biot-Savart involves a 1 over r squared term, so I could say 1 over r squared is equal to cosine squared of theta over a squared. So going back to Biot-Savart's law, dB is equal to, bring these two things down, your constants out here, mu naught over 4 pi times I, can't forget the current, Now I've got this cross product that is here, and it is negative a secant squared theta cosine theta d theta k hat times 1 over r squared, because you're basically multiplying this by 1 over r squared. So this is times cosine squared theta over a squared. So now we just need to simplify things. Now, maybe you remember that secant of theta is 1 over cosine of theta, so that helps things quite a bit because I've got a cosine squared term and I've got a secant squared term. So these two cancel each other out because this is 1 over cosine squared and this is cosine squared. So those two go away. Also, I have the negative sign. You can move that out. And one of this a cancels, and this is exponent is reduced by 1. So dB then is equal to negative mu naught I over 4 pi times cosine of theta d theta k hat. Now the next thing we need to do to find the total field is we integrate. So I'm going to leave all the constants to the outside. Negative mu naught I over 4 pi. And I know we get used to putting the unit vector on the end, but I'm going to move it out here, which is okay, just so I can keep all my integral stuff to the right-hand side. And we're going to integrate from theta 1 to theta 2. So what is the integral of cosine of theta? Well, that's actually a nice one. That's just sine of theta. For 4 pi, my negative, don't miss the negative, k hat times the integral of cosine of theta, which is just sine of theta, integrated from theta 1 to theta 2. So this is where I think it gets the trickiest part. What is theta 1 and theta 2? Well, we start, if we're integrating over an infinitely long wire, then this theta is going to approach 90 degrees, right? So we're going to start at a 90 degree angle and end up at a negative 90 degree angle on the other side. So we start out at a 90 degree angle here, and we end up with a negative 90 degree angle here. Now, it may seem more intuitive to you, and honestly, myself included, if we're moving in a counterclockwise fashion to say, let's start off at a negative pi over 2 or negative 90 degree angle and end up at a positive 90 degree angle. But that's not going to work well over here because we have to start with x being negative. And if you start with a tangent of, if we look at, say, some tangent of whatever, tangent of positive 10, you get a positive number, and so we have to have the negative here to make it negative. If you look at tangent of negative 10, negative whatever, you get a negative number, so this negative could not be there because the x has to be negative from the beginning and end up positive. So somewhere there's got to be a negative there. If you insert the negative here, then you must integrate from positive pi over 2 to negative pi over 2. These things have to be consistent. So I can say this is from pi over 2 to negative pi over 2. Now I could take that negative sign and absorb it into the integral, into these integration limits by flipping them. I think that keeps things a little neater, but people often get angry when I do that, so I won't do that here. So mu naught I over 4 pi k hat times sine of negative pi over 2 minus sine of positive pi over 2 . So negative pi over 2, what is that? That's negative 1 minus positive 1. So that's negative 2, right? And if you have a if you have a negative here, negative there, they cancel. So B equals positive mu naught I over 2 pi. Where the 4 go? Well, because I've got a 2 from here, so that cuts that down. K hat. And of course, this should come out positive. It has to be positive because the direction given by the first right-hand rule of this cross product says that the magnetic field is going to point your fingers in the direction of ds, curl them in the direction of r hat, and the field must point up out of the page, positive k hat direction. So we should have gotten a positive answer. Now, if we talk about the second right-hand rule, the thing to come, a slide later in the presentation, the second right-hand rule says point your thumb in the direction of any current, and your fingers will curl in the direction of the magnetic field around that current. So my fingers are curling up and out of the page on that other side. If I were to look at a point down here, it would be the exact opposite. It would be pointing down into the page.